of a kernel that is instruction bound, actually. So what this morning said that there aren't that many kernels that are instruction bound. This, if you use constant memory, then this kernel is definitely instruction bound, because if you look at it, all the threads only read two floating point values, like the x and y position of the point that they are checking, and then you have this this constant memory that stores all the vertices, but that is very fast. All the threads are accessing the same values, so that barely counts towards your bandwidth usage. But then it's using the two floating point values that it got from global memory. It's using them more than 600 times. Well, how often do you get that kind of arithmetic intensity? So this is
hardly ever.
Yeah, exactly. So this is a perfect example of a compute-bound kernel. So yeah, let's So let's continue with the solution to get everyone up to the same level. So inside the pnpoly.cu file, we have added a constant variable of type float2, which is just two floats, right? And we gave it some different name. So in my case, I used a C underscore to sort of tell the reader of this program that it's in constant memory. Then inside the kernel, I have, of course, these two values that are read from constant memory, and they should use my self-made-up name for the constant memory array, rather than the array that is actually passed as a kernel argument. Right? And you can access it directly because it's a global variable inside your program, so you can just, there's no need to change the arguments to the kernel. Then if you were using the C API, then all you need to do is add one call to the mem copy to symbol function, where you specify the symbol that you are copying to, and also the array from which you are copying, the amount of data that you will be copying, and one new parameter, that is the offset into this constant memory array. It's a mandatory parameter to this post memcopy to symbol function. It's a bit confusing why it is there, but yeah, it's basically there because we have this awkward interface to actually create these things. So in many programs, if you have a lot of constants that you need to pass around, then it's often nice to just create one constant array that is the maximum size of your constant memory, and then do everything yourself with offsets. It's ugly and it's a nightmare to debug.
But why do this?
If you have a huge number of constants, then it's something that you would do.
So it's for performance reasons, to instead of
well, for managing code reasons, in a sense, for programmability, or if the number of constants is varying as well. It could be. I used to work with an ocean code that had a huge number of parameters that were sort of constant in this sense, because they were basically part of a scheme that fitted a particular. Well, let's not go into too much detail. But it has a fitting model, a parameter fitted model for the buoyancy in the vertical dimension within the ocean, and so there were many parameters like 34 something. So then it was more convenient to define one array with the 34 constants than to define 34 variables.
And 34 mem copies.
Yeah, because your code kind of explodes. So,
yeah, okay.
It's both ugly, definitely. So that's the C part. In Python, it's actually a bit nicer, I think. There's one thing though, we have to first look up where our variable with this particular name went, because this is inside the C code. Yeah? And that C code is read in as a string at the top of our Python file, and then we pass it to this source module object. And what source module is actually doing, it's compiling the code, and it's also uploading the compiled object to the device. And then PyCUDA basically has a reference to this compiled module and I conveniently named that module, that particular object. And to that object we have to ask, hey, where did you leave my variable with this name? And that's why we have this get global function in there. But once we have obtained the address, notice that I'm only using the first part of what get global is returning. So once we have obtained that particular device pointer, the nice thing about CUDA, PyCUDA API is that we can just use the host to device memcopy in the same way as if we were copying to global memory or to constant memory. So that's actually a bit of a better design in a sense. That's the solution. Any questions about that? Okay, great. Then we can continue with an even more confusing memory space. If you thought constant was something crazy to wrap your head around, then be prepared. This is shared memory. And shared memory is rather special. Shared memory is shared between threads that are in the same thread block. So this is, if you were wondering, why do we actually group these threads into thread blocks? Because we index them globally anyway with our index that we computed in vectorhead. This is where thread blocks are going to matter. Because only threads from the same thread block can actually read and write to shared memory. And shared memory is in many ways actually basically the only way that threads within a thread block can communicate with each other. There's also something else called warp shuffle instructions, but I'll not go into it.
It sounds like a bad Doctor Who episode.
Yeah.
Warp shuffle instruction.
Yeah, that's, you should see it like that, basically. Quite an accurate description, I think. But, yeah, so for now, consider shared memory the only way that threads within a thread block can communicate. And so what does it look like in the code? Let's start with that. Yes? No, that's the only thing that you can communicate. Threads from different thread blocks have no way of communicating with each other. You should basically see it as that threads from different thread blocks are completely independent, and we cannot synchronize them. That's something that...
But we just have this constant and then this global variables, right?
Yeah, sure. They can all read it, but they cannot communicate through it.
Right.
We cannot communicate by a book on the table. That's,
Wait, but alright. Shared, we have shared, we have constant, and we have global.
yeah.
And global is only for reading also.
No, but global is also for storing the output after your kernel is executed.
But it's, yeah.
It's the
It's
only way.
non-coherent.
After it's executed.
Yeah.
Exactly.
Yeah. So while a kernel is running, we have absolutely no way for threads from different thread blocks to wait on each other, depend on each other, read each other's output or something. That's impossible. Yeah. But shared memory is somewhere in between that, in the sense that within a thread block, threads can, through shared memory, can actually collaborate. Yeah, so, and that's why inside the kernel code, you see the shared qualifier here, and it's actually quite a peculiar qualifier, this shared qualifier, because now I have this kernel, and this is actually a histogram kernel, so I have some values that are under the pointer values, and I want to put them into a number of bins. And those bins, I'm going to collect them inside shared memory first. And in the end, we will be writing the output to output in some manner. Doesn't really matter for now. But I declare, in my kernel, I declare this shared int. So I have an array equal to the number of bins. Then I'm going to call that shared output, because that will be the output of this thread block together, basically. And so I declare this shared memory array. What happens, actually, is that threads within the same thread block, so threads that are from the same thread block, they will see the same memory. And this is actually something that is quite weird if you think about it, because we were writing a program on the abstraction level of a thread. But now in here I have a single line that is actually not about the thread, but about the thread block. It defines this data structure on the level of a thread block. And all the threads within the thread block will see the same memory. So if I write to the very first location in this array, then the other threads will be able to read that at some point. I'm saying at some point, because the memory is again not coherent. But there's one thing that's called sync threads, and that's what we can do to make sure that the writes that happen before sync threads will actually become visible to the other threads within the thread block. So sync threads is what we call in parallel programming, we call a barrier. All the threads within the thread block at some point come to this point where they see sync threads as an instruction, and they will wait in that part of the code until all the threads in the thread block have reached this point. So in that sense it's a barrier, right? Everyone is waiting until all the threads have called sync threads, and only then all the threads will execute again in parallel. So it's what we call a barrier. And only, so if you write to shared memory, then only after the barrier can you read that value from shared memory. And that's very important. So you see it also here in the code, where in this case an atomic is used to write to shared memory, but those writes will only be visible to the other threads once we have called sync threads. So we want to make sure that all the threads have passed that point, because only then after that we can trust the output, because then all the threads have actually performed their input.
What does atomic add to? Because it also needs to read, right?
Atomic add is a special atomic instruction that, in this case, increments the value here with 1.
But is that the value of the shared?
Yeah, the shared
So
value.
it does have to read it then, right?
Yeah,
to
yeah,
something.
but it's atomic, so it's special. Yeah.
Yeah, and it doesn't matter in which order.
Yeah, yeah. And also, because this is an atomic, it doesn't mean that we can leave out the sync. Right? Because only after the sync, we know that all the threads have executed their atomic instruction. So don't be fooled by atomics. you still need that sync threads, because otherwise, if some thread, here in the code, if some thread starts writing output, so well, I have atomics, I don't need synchronize, and I can just write the output, but then you start writing the output before the other threads in the thread block have actually performed their input. So even with atomics, you will still need to synchronize. Yeah, so a little bit more about shared memory. The size in most situations has to be known at compile time, just like with constant memory. It's in the scope of the thread block. So all the threads in the thread block see the same memory, but threads from different thread blocks will see a completely different memory space. So if you write to location 0 in one thread block, the thread from a different thread block will not see that value appearing ever in location 0. Right? So they will see just different memories. They will see a different addressable space. And it's also not initialized, so if you want to do anything meaningful with it, then you first have to fill it with values. It also means that sometimes you need to fill it with zeros if you're going to accumulate something. It's also not persistent, so it's inside your function, and if your function ends, then your shared memory is also gone. If you want to retain those values in some way, then you need to write those values to global memory. So that's what you will often do. You will, as a thread block together, produce some values. You will start to accumulate them in shared memory and then write back the output to global memory. Or what you could do is, if you have threads that need to do similar work but on different data, they can together fill the shared memory with all the inputs that they will need, all the threads in this thread block will need for their computation, and then perform that computation, but only on the data in shared memory. This is really the cache usage, where you basically use shared memory as if it is a software programmable cache. and only then all the threads will write their output, but not necessarily first to shared memory. So they're basically two different uses. Either you will together cooperatively compute something, or you will just use it as a software programmable cache.
So,
Yeah.
In this example with the histogram, it's in the output is not initialized, right? So this is not.
Yeah, I left out
Oh, okay.
quite
okay.
a bit.
Yeah. Okay.
Yeah, it's just to give you an impression on
But if I would run this, the result would be
undefined.
yes.
Yeah. There would actually be no result because we never store shared memory.
No. Yes.
So how does atomic add and shared memory impact performance?
Quite a bit. Yeah. But the advantage here is that as long as your data is rather well distributed, then most of these atomics can actually operate on different data, so they won't hurt each other. But if two threads have to add to the same bin, then these atomics will have to be, these additions will have to be serialized, of course. Yeah.
So the atomic add only makes sure that the add is actually a transaction, right? It's,
Yeah, that the adds don't interfere
so
with
they
each
don't
other.
interfere with each other. Doesn't say anything about the ordering. It's a completely different issue.
Interfere, you mean that you will interrupt the operation.
Yeah, you could.
Yeah, well, if you just have a normal addition, then what could happen is like what Daphne said, threads also, if you want to add to something, you also have to know what is something. Right? So if you would actually write that out, you say, okay, what's the value in this bin right now? Okay, I'll remember that value, I'll add one to it, and then I'll write this value. And if you do it like that, then both threads, two threads at the same time, they read that value, they add one, and they write the same value to the same location. No issues whatsoever, except that you have only added one instead of two. So that's why you need atomics in this particular case, or in any case where you want to write to the same location, you have to do some kind of synchronization.
Look in the location, nobody else can use it well, for instance.
You could see it like that.
Yeah,
I'm not going to.
it's like volatile in Java. If you know Java. Python, yeah, I don't know.
Being muted.
Python is a global hook, right? So it doesn't have any.
You don't have to.
I guess, yeah.
Okay. I have another example about shared memory, because it's actually, we're going to use shared memory in the third hands-on, guys, if I may. We're going to use shared memory in the third hands-on session. But before we go there, I thought it would be nice to have another example on how to use shared memory. In this case, we're going to use it as a sort of a cache. This is a transpose kernel, which is taking a two-dimensional input and a two-dimensional output, and of the width and the height are actually stored in these parameters as well. So we have H and W to specify the width and the height of the input. The width and the height of the output will actually be flipped, of course. So then this is basically an example kernel of how you could use shared memory for doing a more efficient transpose. Because you could, of course, just read the input and then write that to a different location in the output to perform your transpose. But what will happen then is that threads that are next to each other in the x direction would read the input and then write to completely different values in the output. Sorry. So when you transpose a two-dimensional data structure, you first have values that are on a row, and that row will become a column in the output. Yeah. So your memory, I'll also talk about this later this afternoon, but your memory is optimized for reading in rows. So if you, in this case, in the way that is currently in this code, if you read the input like this, then that's a good way of accessing the data. Because if you look at it, I and J J is actually the index in the x direction. So threads that have adjacent x indices will actually access adjacent locations in the input. But if you would use directly those I and j to write the output like that, then the threads will access values that are h apart if they have adjacent j values. So they will access the column rather than the row. And that's a problem. So what we are going to do now is we are going to allocate a two-dimensional area of shared memory equal to the size of this thread block. So I'm assuming that block size x and block size y are compile time defined constants that match the thread block size with which this kernel is launched. And so we declare a two-dimensional array of shared memory. In the first step, we fill the shared memory with the area that this thread block is responsible for in the input. Then we call sync threads to make sure that all the threads are done with filling the shared memory. And then we do some very interesting index computation. And then we can write the output. And notice that the x and y's here are intentionally flipped, and also y, I and j are redefined here, basically switching x and y to make sure that what were used to be a row will now become a column. And I'm not going into the details of the index calculation in this particular example because transpose is actually something that you can really break your head on. But this does give you an idea of, oh, okay, so that's how I can use shared memory. You define it, you fill it with values, and then you call sync threads to make sure that all threads in the block have come up to this point, and then we can actually store these values. Now the advantage is that basically what happens is that threads will write a value different from that they have read. Yeah, so this thread block is really collaborating. All the threads within this thread block are cooperating with each other. They fill a particular part of, they fill shared memory with a particular two-dimensional area from the input in a way that all the threads that have adjacent x indices that they write and that they read adjacent locations from the global memory. And then we reorder our indices in a way that threads with adjacent x indices, as you can see from this I here, and I is defined as the thread index in the x dimension. So again, threads with adjacent x values will write to adjacent locations in the output. So again, using the fact that our memories are optimized for row-based access. Don't use this kernel in reality, because if you want to do this absolutely right, you need a whole lot more if statements and bounds checking. And in this particular fashion, you will also get something that is called shared memory bank conflicts, which I will not go into today. But yeah, this is basically, I think, an illustrative example.
That's only a performance problem.
Those are the only performance, right? So, yeah.
And do you get into trouble also because only the threads within thread block can use the same?
No, in this case, that's not a problem. No, because
It's the same block.
yeah, technically we have a particular area that this thread block is responsible for in both the input and the output, and that is matching. Yeah. Okay. Then we can go to the third hands-on, which will be quite different from the transpose that we've just seen. But in this case, the threads are collaborating with each other. They together have to produce a single result. So if you can go to the directory reduction and look at the code. Now the idea is that you implement the kernel, and actually most of the kernel is comments at the moment, so you will have to read through that. I don't think you need to change anything in the host code. No, it's just working the kernel this time. And you have to change or implement the kernel because nothing is there yet, almost nothing, such that the threads compute a sum, but they compute a single sum as with the thread block as a whole. Right, so at the moment we start with a large array, and the goal is to reduce that to a single value. And what we need to do then is, what is already implemented for you is that all the threads from all the thread blocks together, they together iterate over the input array. So all the threads, they take huge steps in the input, and what they do with every value that they encounter, they add to their local sum. So they start, all the threads start with the thread local register that has a 0 value in the beginning, and then they will add the value that they come across in the input. So they will sum multiple values in the input, and then what they basically have is a partial sum. And so all the threads after this stepping, they have a partial sum of the input. And what we then need to do is within the thread block, we need to combine these partial sums, this thread per thread partial sums, into a per block partial sum. Because that's the only thing that we can do, right? We cannot synchronize with the other blocks, but at least within a thread block we can come to a single value by using this shared memory in a smart way. And that's what we will do. Then if you read through the host code in this example, you will see that the kernel is actually called twice. And that is because at the end, all the threads, or basically every thread block, will store its single value into the output array, called out array, using its block index. So all the thread blocks will output a single per block partial sum to the output array. And then the kernel is called again, using the output from the first kernel in the second kernel, and then the number of elements that need to be summed is actually equal to the number of blocks that executed the first program. And if we then run the kernel again with only one thread block, then we can get to a single value. So that's why you see 2 kernel calls inside this program. But now it's up to you to implement basically the kernel a little bit before the kernel starts and before the main loop of the kernel, and then there's also a loop inside the kernel, but that's all explained in the comments. So you need to implement what is in the loop to make sure that the threads within a thread block sum these values. There's one special thing basically, that is that we assume that the number of threads in the thread block is a power of 2. You will also see that inside the code. It's just a statically defined, so like hash define block size x. I think I'm using 256, so you can see that in the code. You can assume that that doesn't change. If you have any questions, let me know. Martin?
Yes. I have a question.
Offline? Yeah. Okay.